Good morning, everybody. My name is Nick Rivera, and I'm a PhD student working with Professor Marin Soljacic. And today what I want to talk to you about is a really exciting new idea we have to solve a big open problem in quantum science and technology related to the deterministic generation or preparation of macroscopic quantum states of light with a special focus on Fock states. And besides the special focus on Fock states, another exciting thing that we worked out that we want to show you is how to design nonlinearities that select for different kinds of macroscopic states of light, like Fock states, going beyond the paradigm of doing things like generating squeeze states. So let's begin. This talk is about Fock states. They're fundamental, they're important, and they're hard to make. So why are they fundamental? Well, they're the eigenstates of the electromagnetic field. Consider a single mode resonator with Hamiltonian h bar omega a dagger a. Its eigenstates are the number states, or the Fock states. And this number can be anything from 0 to infinity. These states have a very well-defined photon number and also a well-defined energy. And so in that sense, they are the most basic states of light from a quantum mechanical perspective. But despite being so basic and fundamental, they're incredibly difficult to make. And I'll get back to that in a second. But this is a bit of a shame because they have a lot of really potentially exciting applications, but are also really interesting just from a fundamental perspective. So in terms of applications, Fock states can be used for quantum algorithms. If you want to simulate this vibrational electronic spectra of a molecule, you can encode the results in Fock states, do manipulations on them, and then read out the results and do a quantum simulation. They're also considered an important resource for linear optical quantum computing. And Fock states, because they have no photon number noise or no intensity noise, you might imagine that they have some natural applications in metrology and spectroscopy, where if you had a large Fock state, you'd have a really high signal and no noise, which is sort of an absolute maximum signal to noise coming from intrinsic photon fluctuations. Fundamentally, I mean, they are the most basic state of light. It would be good if we could realize them. And they have no classical counterpart whatsoever. These are truly non-classical states. They have negative phase space representation values, all of that. They're a workhorse for generating other more complex superposition states. Like you could think about trying to leverage Fock states to generate Noon states, multimode Fock states, cat states, and the like. And kind of what excites me a lot, and it's hard to put an exact application value to, is just the fact that you're bringing you're bringing quantum mechanics to the macroscopic world if you can generate large Fock states. And we don't have a lot of examples where there's something macroscopic in quantum, but some of the few examples that come to mind, like Bose-Einstein condensation and superconductivity, are extremely consequential from both an applications and fundamental perspective. And so I think large Fock states are somewhat similar in that respect. But they're super hard to make. There's kind of two things at play when saying that they're hard to make. One thing, and we'll address that in this talk, is that there are very few mechanisms that naturally select Fock states. And I'll talk about this a little bit later, but keep in mind that if I have a second order nonlinear crystal like a Chi2, I can generate squeeze states, and it's sort of the natural result of the Chi2 interaction Hamiltonian. There is not a similar interaction Hamiltonian that will just want to generate large Fock states, and so you have to get kind of creative, and people have. The other thing is that they're pretty fragile in the presence of loss or gain. If you have loss or gain, then you have absorption and or stimulated emission happening at uncertain times, and that is going to spoil your Fock state and create quite a lot of photon number uncertainty. And so what have people done? So kind of the most amazing stuff so far has been at microwave frequencies, where people have been able to generate Fock states in the order of 10 to 15 photons. And so the basic idea is that because they're fragile in the presence of loss, you need to build up these states before any loss is set in. So you have a cavity, you have something that's putting photons in the cavity, you want to do it deterministically. So in practice, what people do is coherent control experiments or superconducting qubits, where they send in these complicated pulse sequences that, because of interference, ensure that you're building up a Fock state, but you have to do all of this before a photon can leak out of the cavity. And so that sets an ultimate limit on how large of a Fock state you can generate. And that's kind of the idea of all the microwave applications. In optics, you can't do any of that. You can't use strong coupling, coherent control, and cavity quantum electrodynamics to generate 15 photons before the cavity photon is lost, both because your strong coupling scale is a little weak and because your cavity photon is lost a little too quickly. And so it's hard to generate Fock states deterministically of more than 2 photons. The way people generate Fock states of 1 photon, you can imagine a quantum emitter or heralding parametric down conversion pairs. And this is kind of part of a larger problem of how we generate macroscopic quantum states of light in the first place. I think one of the most famous examples, and one of the very few, is squeeze states. We know it's possible to start from the vacuum state, have a Chi2 interaction, and then generate a squeeze state with a lot of photons. This is called bright squeeze vacuum. There are people using this stuff to try and enhance nonlinear effects and do things that leverage the sort of quantum statistics of large squeezed light. But we've known for a long time that you can use Chi2 crystals and also Chi3 systems to generate squeezed light. Let's think about Chi2 for a second. So I like to say that Chi2 naturally selects squeeze states. The reason is that you have this interaction Hamiltonian, which is cubic in creation and annihilation operators. And if you come in with a pump, then you're turning one of those electric field operators into something parametric. And so you have a time varying parametric pump multiplied by something quadratic in creation and annihilation operators. And on resonance, we know if we exponentiate that we will get squeeze states. It's pretty natural. And you have to deal with losses and all this complicated stuff, but at least the interaction is trying to do that. The big question, and one that I want to start addressing in this talk with our early results, is, well, how do you make a nonlinearity that would want to produce macroscopic Fock states? And so that's really where we're going now. I want to tell you about our proposal to generate macroscopic Fock states using special sharply intensity dependent nonlinearities that have to be sort of synthetically created and created under exotic conditions. And I'll also show you that because of the way we're generating these states through, I guess, what I'll call laser interactions, these states can actually be stored indefinitely because they're actually non-equilibrium steady states of the system that we're proposing. So here's the idea. The concept is called the Fock laser, so that I'll use that as a shorthand for what this is. And the Fock laser looks a lot like a laser. We have a pumped gain medium. This gain medium may be subject to some kind of non-radiative relaxation dynamics. The gain medium is pretty generic. You can imagine a solid state 4 level system like ND-YAG. You can imagine molecular dyes, gases, semiconductors. It should all work. And it's interaction through stimulated emission and absorption with a resonator, just like in a laser. This resonator is subject to internal losses and also external losses associated with leakage into the far field. And the key thing for us is that this cavity has to be nonlinear in just the right way. So by nonlinear, I mean, we all have some idea, it has to be a nonlinearity of the Kerr type. So you have some idea, okay, the refractive index depends on nonlinearity. I'm using a more general definition of a Kerr type nonlinearity, which is really just to say that the relevant eigenstates in the problem are Fock states and their energy depends on the number of them that you have. And so the energy of n excitations or photons will be some function of n times h bar omega, which for a nonlinear system will be a nonlinear function of n. For a linear cavity, f of n is just n. And if you want an example to think about concretely, think about a Kerr Hamiltonian in a single mode case describing something like self phase modulation of a resonator mode, where the energy of n photons is h bar omega times a term linear in n plus a term quadratic in n. And so the energy of a single photon, which is the excitation energy from n-1 to n photons, is proportional to n for weak enough nonlinearities, which is usually the case in Kerr nonlinearity. So the key additional requirement is that the nonlinearity has to be sharp in some way, so that when you change the photon number by 1, this causes a big enough change in the energy of a photon so that the gain or loss is rapidly changed. And you might notice that I just introduced a new condition so that this doesn't just depend on the strength of the nonlinearity, but also the bandwidth of the gain or loss. If my gain was infinitely sharp, then a change of 1 photon would immediately change the gain by a ton. But we know no gain is infinitely sharp, and similarly, no loss is infinitely sharp. So there's two things at play here: the strength of the nonlinearity and the bandwidth of the gain or loss. And so let me just show you kind of the behavior of an ideal Fock laser. So to understand it, you need to understand the rate of stimulated emission and the rate of absorption. And by absorption, I could mean just generalized absorption like leakage, where a photon from the cavity is absorbed by the far field propagating beam. So we're using nonlinearity to force a specific behavior of the intensity-dependent stimulated emission rate, R emit, from n to n plus 1, or n-1 to n. And so let me just review the normal case of a 2-level laser, or a gain medium, which is effectively 2-level coupled to a cavity with a partially transmitting end mirror. So in that case, the rate of stimulated emission is given by the saturable gain expression. So you have a linear term, a times n, where a is the temporal linear gain coefficient, divided by 1 plus the photon number divided by the saturation photon number, and the saturation photon number is proportional to the saturation intensity. The loss, on the other hand, is just linear. It's kappa times n, where kappa, if we only have radiative leakage, is basically the cavity frequency divided by its Q factor. And so we can go ahead and plot those things. So that's this guy up here. So the blue is the saturable gain and the orange is the loss. And the point where they intersect, where the gain balances the loss, dictates the steady state mean photon number. From these rates, though, it's actually possible to also say what the probability distribution is to have different numbers of photons in the cavity. And when you're well above threshold, in other words, when A is sufficiently larger than kappa, this photon probability distribution converges to a Poissonian distribution corresponding to a coherent state with randomly uniform phase. Now, let's talk about the Fock laser. The Fock laser is a lot like these, but just with one difference. So it's the same, except I'm also going to stipulate that when n is greater than some critical number n max, the rate is just 0. So that, you know, it's basically as if I plotted this and then at some point just cut it off. Here I didn't plot it with a saturation photon number, but it doesn't make much difference for the plot. So you have some kind of gain and then it abruptly drops to 0. And this is not going to be as contrived as it looks. I'll actually show you a real physical example where this can happen. But in this example, it's pretty clear that on the right side of this quote unquote wall, you don't expect to have any probability for photons to be there. So you're compressing the photon distribution towards lower photon numbers. However, when you have net gain, which is anywhere where the blue is greater than the orange, the distribution is getting pushed towards the wall. So what ends up happening is that basically you're squeezing from both sides of the photon probability distribution. And when you're sufficiently above pump, and I mean, when your pump is sufficiently above threshold, say by a factor of 2, you'll converge to something that looks quite a lot like a single excitation with a Fock state with many excitations in it. So now let me explain to you how we implement that, because I mean, that drawing looks rather contrived. It's kind of clear that it should work, but the much bigger question is what system could even do it. And so I'll now show you how recent progress in a field called deep strong coupling actually enables this kind of thing. But since deep strong coupling is rather new, I'd like to motivate it by talking about strong coupling first. So, you know, what's the game we're playing here? We're trying to create pretty strong and pretty sharp nonlinearities. And if you want to create a strong nonlinearity, a two-level system is an incredible example of this, right? It's a system that can maintain only one excitation. However, I mean, so that's really nonlinear, but it's not very photon-like, and you can't put many excitations in it. So that's kind of the problem. You also can't have coherence between different excitation levels, so that it's missing quite a lot. However, you can use it to make a photon rather nonlinear. By strong coupling it to a cavity. So if I have a two-level system of transition frequency omega naught coupled to a cavity at frequency omega naught, and they're interacting through the Jaynes-Cummings interaction, then we know that there will be degeneracies that are split by the Jaynes-Cummings interaction, forming upper and lower polaritonic states for each exit. So there will be a manifold indexed by an integer of upper and lower polaritonic states. So there will be an upper and lower polaritonic 1 state, and upper and lower polaritonic 2 state, and so on. And they'll have splittings that increase with the excitation level. And so this leads to anharmonicity at the 1 photon level. It leads to the very famous effect of photon blockade, where I can excite the system from 0 to, say, the 1+ state, but I can't excite the 1+ state to either of the next states because my photon is off resonant with the next transition. So it's clear that you can use stuff like that and have a steady state with 1 excitation in it. But it's very unclear how you would do that to have a steady state with n excitations in it. You want something like n photon blockade, where the system would easily accept n excitations and then not accept the n+1 excitation. So that's kind of a verbal representation of the drawing from the last slide. So the interesting thing that I'll show you now is that when you take these strong coupling systems to their limits and you make the coupling very strong, this n photon blockade naturally arises. And so this is related to the idea of ultra strong and also deep strong coupling, which is something that's been really a hot topic, especially in superconducting qubit implementations where this is actually possible. So the situation is this: in superconducting qubits, you have this qubit with a transition which has a very large effective dipole moment in a sense, and so the vacuum Rabi frequency, which is proportional to that dipole moment, is really large. And in fact, unlike strong coupling, where the coupling is larger than the losses in the system, here the coupling is either comparable to or actually even larger than the transition frequency in the system, which means that the interaction energy scale becomes the dominant energy scale. And in this limit, quite a lot of interesting stuff happens. So basically, within the past 2 or 3 years, people have been able to realize couplings larger than 1 and couplings of nearly 2. When the coupling is larger than 1, we call this the deep strong coupling regime, because really it's the interaction that matters the most, and you can actually neglect the energy of the qubit to a first approximation. And people have realized these things in systems of flux qubits, either coupled to LC resonators or microwave waveguides supporting a continuum of modes. So let me tell you about the physics of deep strong coupling, because we're going to need it. So the system, imagine a flux qubit coupled to a microwave resonator, like an LC resonator of some type. And that's going to be coupled to, so the coupling is going to be mediated through the Rabi Hamiltonian. I'll skip some terms in this that are not too important for us right now. So we have the energy of the qubit, which is the sigma z term. We have the energy of the cavity, which is the h bar omega a dagger a term. And then we have the interaction, which is proportional to the vacuum Rabi frequency, the sigma x of the qubit, and basically the electric field of the cavity, a plus a dagger. And in the deep strong coupling regime, what I said is that you can actually ignore the energy of the qubit. And so instead, you're just left with, you can ignore this too, and you're left with this Hamiltonian. And you can complete the square and immediately see that this Hamiltonian is just taking a dagger a and displacing it with a displacement operator, the one that generates coherent states, by an amount g sigma x. And this is basically just omega times b dagger b, where b and b dagger represent new excitations. And the eigenstates of the deep strong coupling states are Fock states of the b operator. And if you look at the energy spectrum in the deep strong coupling regime, to a very good approximation, the energy spectrum is given by the following expression. So the energy has two quantum numbers, one which is like a spin index. I'll take plus or minus 1. It's not actually the spin of the qubit. It's a little more subtle. And then an excitation level. And that excitation level is parameterizing basically the Fock states of the b and b dagger operators. And so the energies, there's a linear term, h bar omega n. So if I drop this term, I would have something that just looks like photons or a harmonic oscillator. But then I have this other term, which is proportional to the Laguerre polynomial of order n with argument 4g squared. And the way to think about ln of 4g squared is that it's basically 0 if n is less than g squared, and it's very large if n is greater than g squared. And in between, it's kind of exponential. It's basically exponentially growing. And so that leads to a spectrum like what you see here. Here I'm plotting the energy spectrum. So these are different energy levels for different coupling strengths. And what you will see is that, for very large coupling on this plot, the energy spectrum looks linear. You can only see this. But if you go to smaller couplings like 2.5, you see that the energy spectrum looks linear, perfectly harmonic, and then it's not harmonic anymore. You see there are very noticeable splittings in the energy. The eigenstates, I mean, these are really the good excitations of the system. They're the Fock states of B. And so, when I refer to Fock states, I really mean these eigenstates of the deep strong coupling system, which we call deep strong coupling photons. Now, this is really good. We have this kind of like really sharply nonlinear energy spectrum. And now we need to ask what happens when we couple an external emitter representing a gain medium to it. And basically, you should imagine that this external gain medium could be another superconducting qubit, which is coupled to the same cavity, but weakly. And that's possible. It's possible to adjust the couplings of different qubits and to tune them. So you can imagine one qubit deep strong coupled to the cavity and one weakly coupled, which is acting as kind of like a single gain atom. That's kind of the most plausible way to realize this. And so if we imagine it coupling to this deep strong coupling cavity through the field of the cavity, then we can calculate the stimulated emission rate into that cavity. You'll find that there's a linear term, and then there's the saturation, and then there's the detuning between the gain and the deep strong coupling photon frequency, which is constant up to some n being g squared, and then very large after that. So the detuning will grow quite rapidly, and that will cause the gain to decrease quite rapidly. And this is the plot of the stimulated emission as a function of n. And you can see it basically does what we did in that drawing. So it grows linearly and then decays, and then it's basically 0. It has these oscillations, but you can ignore that to a first approximation. This equation is really just textbook laser physics, right? This looks exactly like the susceptibility of a gain atom, where the imaginary part is going to have some constant part, and then an intensity over I saturation term, and then a detuning. And the only difference between this and this is that the detuning depends on energy because your photon is nonlinear. And so that's that's kind of how it works here, and it takes quite a lot to show that it works this way, but you can show also through kind of like ab initio methods that it really does work this way, even with these new gain medium and these nonlinear photons. And the way we went about that is by extending the famous quantum laser theory that under normal circumstances predicts coherent states or dephased coherent states, and then generalize it to the case where the photon is substantially nonlinear. And that's quite a lot of generalization, and it captures quite a lot of new cases, and you can see that in the paper that will come out. Let's kind of stay focused here on the case of the deep strong coupling laser. And so I'll just very briefly kind of explain the basic math here. So what happens is that the probability distribution for the photon, rho n, basically obeys a rate equation, a quantum optical type of rate equation, where the probability of having n photons is influenced by the probability of having n minus 1 photons due to stimulated emission, the probability of n plus 1 photons due to absorption, and also its own probability due to stimulated emission and absorption combined. And there are these rates that are basically what I showed on the previous slide, where you have this kind of nonlinearity, which is partially from saturation, partially from the detuning from the deep strong coupling photons. And we can find the steady state solution. So we can find the steady state probability distribution in terms of a cumulative product of basically this guy divided by this guy. And so you get something like this. And the result, and from this probability distribution, I can tell you the mean number of photons in the steady state, the photon number fluctuations, and just what the quantum statistics or probability distribution of the deep strong coupling photons looks like. And so that's shown here. So here I'm plotting the photon number as a function of the pump rate. And what you can see is that for weak coupling, I have this kind of S curve that you know from laser physics, where below threshold, I have a small number of photons, and then at threshold, the number of photons increases very rapidly and then saturates. But then for deep strong coupling, you see that the system below threshold, which is for anything to the left of 1 here, is following the S curve, but then very quickly just saturates, and the number of photons does not increase no matter how much you increase the pump, because again, there really can't be probability to go past this wall at n equals g squared, and so the probability distribution is just getting pushed against it. And that will cause the photon number fluctuations to decrease. So here I'm plotting the uncertainty in the number of deep strong coupling photons as a function of that pump rate. And you can see for weak coupling, it increases very rapidly at threshold and then goes like square root of n, which is a manifestation of shot noise. But then for the deep strong coupling cases, we follow the same behavior below threshold, but then above threshold, it drops. And these aren't the relative fluctuations, these are the absolute fluctuations. So you really have a situation where the uncertainty in the photon number is going to 0 and you're approaching this Fock state. And you can also see it in these probability distributions of the number of photons as well. In the normal laser, I have this coherent state, Poissonian distribution. And then for stronger coupling, I have these things which look like highly concentrated distributions at a very large photon number, which is basically like g squared. So for g equals 10, I have an 100 photon Fock state. And for g equals 18, I have roughly a 324 photon Fock state. And beyond these kinds of states, there are also all sorts of weird states that I don't know how to generate otherwise coming from this kind of nonlinear interaction. So for example, at threshold, for g equals 10, there's this really interesting uniform state that shows up where the photon probability distribution is essentially uniform up to n equals 100 and then decays quite rapidly because, well, photons can't be supported beyond n equals 100. And then there are also these kinds of states that interpolate between Fock states and coherent states. And that's actually coming from the fact that you saw those oscillations in the plot beyond the wall. And so actually the system is tunneling over. So another kind of interesting thing that happens in the system is that one way to see the way Fock states are generated is that they're basically the limit of thermal states with negative temperature as the temperature goes to 0 from the negative side. Just to give that a little bit of quick detail, when you have a normal laser, so 2-level system coupled to a cavity based on a partially transmitting end mirror, when you're below threshold, the statistics of the photon are thermal and with some effective temperature, which is related to pump strength. And it has a positive temperature, of course. For the deep strong coupling case, it's kind of like we've created a second wall at n equals g squared, and that we have a thermal state which is coming from the most excited state, which is decaying from the most excited state than the least excited state, which represents a negative temperature. And you can actually see it here quite clearly. I mean, this yellow curve is basically this black or this blue curve, but with a negative temperature. And basically, as the temperature goes to 0 minus, the probability distribution is going to coalesce around just the most excited state, g squared. And so we basically form these negative temperature states. And very quickly, all of what I was showing you is analytical and this kind of mechanism for generating Fock states. This is all our idea, so you can be very skeptical about it. I'm skeptical about it every day still, even though it's been a while. But It's pretty robust. Like, you can relax a lot of the assumptions and a lot of the analytics and just try and run a numerical simulation of a Hamiltonian and see what steady state it reaches. And it really does do everything I say. Like this Fock state generating mechanism with this nonlinearity, that's real. The fact that you generate a Fock state from it, that's real. The fact that it's a steady state, that also pans out too. And that's really significant that you can get something like this from numerical ab initio simulations where you relax all the assumptions. In terms of experimental realization, as I mentioned before, kind of things involving superconducting qubits, one deep strong coupled and one weakly coupled. I think that's the most exciting implementation because it's integrated and can really already realize the parameters to realize some of the results shown here, at least for the smaller G's, like 2 or even 3. But we're an optics conference. You probably sat here wondering, how will you do any of this in optics? There's like no path to doing ultra strong or deep strong coupling in optics with a single emitter yet. So yeah, I mean, that's not something you can do, but there actually is something you can do to try and simulate those kind of really sharp nonlinearities in kind of a clever way. So that's something that we figured out, and we're currently building and running that experiment now. And well, that's something I hope to tell you more about next time. And with that, I want to thank you for your attention. If you have any questions, I really appreciate hearing them, and I invite you to check out some of the other talks from our groups. Thank you.